So welcome back. To those of you who are watching this on YouTube, or those of you who were here in person, sorry for these bad jokes. But as you'll note, the schedule is a little bit different. What I wanted to do was get some more, so next week we're going to do technical prerequisites, and then the 2 weeks after that will be maximum likelihood estimation, and then how we use maximum likelihood estimation with missing data. And as you get into it, you're going to realize that part of that is many of you have learned linear models, right? Everybody's learned linear models, regression. So if I ask you in R, hey, I've got X predict Y, which function do you use? LM. How does LM estimate our data? What method does it use? Anybody know that? Ordinary least squares. Unfortunately, that's less flexible than maximum likelihood. Turns out, in this regression approach, we could actually trick it to probably work for us, but we're not going to. We need something maximum likelihood. The main reason for it is if you have missing data on your X variable, what happens in least squares? It's gone, right? X and Y. That's bad. Our goal is to keep all the data that we can. And when we listwise delete, we induce potential for bias, particularly if our data are missing at random, which we'll talk about here today, right? So what do we do for maximum likelihood regression? Linear models. How many of you have done maximum likelihood in linear models? I bet you have. Yeah. What package or what program? Yeah. Like Elmer, LME4, and LME. Yeah, those. Yep. No, it's good. It's good. Um, those will do that, but there's only one outcome, and you have to sort of trick it to give you more than one outcome. Because what we're going to end up doing is showing that when we put X into a likelihood itself, so when we give X part of the actual model, because in least squares, X is just given, right? It doesn't have a distribution. It just goes away. Listwise deletion happens. But when we put it into the model, when we put it into a likelihood, then we can use maximum likelihood for it. And that's really difficult and sloppy in programs like Elmer, where you've got one outcome variable. You have to you can do it. You have to create dummy codes and like really twist the logic. And then there's some models that are just not possible. So instead of that, we're going to do path analysis software, Lavon, right? Many of you may have seen Lavon before, but I'm not assuming everybody has because it's not a prerequisite. So that's where we're getting to with this section of the class right here. And because I don't want to just say throw words at you without having like how to do it, I thought it'd be better to slow down a little bit and cover some of the prerequisites. So again, many of you may already know that, but that's okay. If you do, then you can critique my teaching or you can take a nap. I don't care. But for those of you who don't know it, I want you to know it, and that's what's important to me. So, sound good? Cool. Any questions on that, I should say? Sound good is like I'm looking for affirmation. I don't need your affirmation. I need to know if you have a question. Okay, that one's it. Also, you'll note I have a homework assignment that is just coming out at 12:30 today. I didn't want to scare you with it ahead of class, so there'll be an announcement on Icon for the homework one. It's due February 11th, which is actually a Friday. So you have a little over 2 weeks to do the assignment. The assignment is going to be, up to this, basically what we've covered up to this point, which is parts of chapter 1 that I didn't talk about today. Auxiliary variables would be one of them. And so there's a data set, there's some auxiliary variables, and I'm only asking you to correlate those with variables that may have missing data, which means listwise deletion. It's sloppy, it's not efficient, but I didn't want to go and teach the method that was talked about in chapter 1 with the latent variable approach. So I felt like that would take an extra amount of time. So this is sort of a cursory glance as to what auxiliary variables happen to do. And we're going to say why that is. We're going to see why that is when we get to maximum likelihood. Okay? Okay. With homework, please note I am open to questions. My office hours, where to find me. I welcome every question, and if there's something in homework that I didn't explain well, please let me know so I can try to explain it better. Okay? All right. Then finally, you can see the reading schedule here. Once we get to you'll have chapter 2 and chapter 3. Actually, I need to move this. Chapter 2 is really going to span 2 weeks here, but I'm going to ask you to read it. There'll be a reading assessment due before next class on chapter 2, and there'll be another reading assessment on chapter 2 after that. So I will change that schedule. All right. I think that's the preliminaries. Any other questions or comments? Okay. So today I'm going to cover things that you read about, but I want to talk about them and have a chance to talk about them with you to see if there's any misconceptions about that or anything that I can clear up for you. So it's going to be a little repetitive today. Not every lecture is going to be like that, particularly when we get into next week when we start talking about technical prerequisites and then maximum likelihood estimation. I want you to understand what it is and how it works. And so we need a little bit of mathematical statistics, just a little bit. And then, because that's sort of the language in which you see likelihoods written. And then we're going to talk about how we build the likelihood, and then we're going to do the likelihood itself. And actually, there's kind of cool thing about it. When we get to chapter 2, you'll see Craig Enders talks about 2 methods for building missing data analysis. One is sort of the joint model approach, which the path analysis software does pretty well with, and one is sort of taking a model and factoring it into taking a joint model and factoring into marginal and conditional distributions. That's why I'm talking about this. That latter part is really hard with maximum likelihood because you'd have to basically code an optimizer yourself. There's no one package that easily does it. But when we get to Bayes, you can. So mainly because the way that Bayesian software works, you have to code it anyway. So it's a matter of putting multiple distributions there. So I'm hoping this will be a little bit more, these changes will be a little bit more, will bring you a little bit more how to do this. Because when I read the chapters, even though he's very good at describing how to do it, I didn't feel like there was the, all right, now do this, now do this, now do this example. Does that make sense? I want to do both. Okay. Any questions for me? Okay, the other thing I forgot to mention is this is a long class, right? And I can never tell whether it's better to teach 2 hour and 15-minute sections or one big one. But that means we're going to have breaks. We're going to have 2 breaks, right? 20 minutes past the hour for 1 o'clock and 2 o'clock, we'll have a break. That'll make our 3 hour and 20-minute class period roughly the same size as we need to be to make it. This is it 3:20? No, 2 hours, 50 minutes will be down to 2:30, which is equivalent to the 2 1 hour and 15-minute classes of the week. There's the math for you. All right? All right. Well, in that case, let's get into the lecture. There we go. Let's see if it'll work on here. I think that's working. Okay. So we're going to talk a little bit about chapter 1, but just sort of the bigger, again, it's repetitive because you read the chapter, but more putting it into better context, maybe your context or maybe my context for missing data. So we'll talk about some of the challenges and implications of missing data in research. We're going to talk about classifying missing data by patterns, which I've never really found that useful, to be honest with you. And then mechanisms for using Rubin's framework, which you all answered questions about. It is warm in here, isn't it? I gotta remember that when I teach. I'll start showing up in shorts or something. But here we go. I've been, as I mentioned, I did this over the winter, and I've been trying to make it not itch. Like I did this a couple years ago and had it on in the summer, and that was a lot worse. And so I'm like, anything I could do to not sweat. And here I am teaching, working up a sweat. It tells you something about my physical fitness. Anyway, we will also talk about limitations of outdated methods today. I like that one a lot because let me just tell you, I'm going to admit to you, my name is Jonathan, and I've used some of those methods. All right. You're supposed to say welcome, Jonathan, I think. Anybody else use any of those methods? Anybody done mean imputation? Yeah, there we go. And we'll talk about design and application of missing data, planned missing data. A little bit of planned missing. I'm not a big fan of planned missing. I mean, there's not a lot to say. All right. Importance of missing data, right? We talked about this a little bit last week. It's everywhere, right? I gave 2 examples last week. One was weather forecasting, right? Another was, particularly in the 2016 presidential election in the United States, we had a lot of polling error. A lot of polls thought Hillary Clinton was going to be elected as president, and that was decidedly not the case. And so those types of missing data I mentioned, if missing data could impact your world like as much as a weather forecast or a forecast about what you're doing, who the next, presidential administration it might be, you can imagine what it might do to your research as well, right? It could possibly be pretty drastic. I mean, last week, nobody expected, how much snow did we get? It was like 3 or 4 inches that day. I think we doubled our snowfall in the year, right? The weather forecast for me was less than an inch of dusting. I was like, oh, that's no big deal. It was a big deal, right? So missing data can bias your results, right? Bias meaning weather forecast predicted less than an inch. We got 3 inches of snow. That's a bias, right? Different than what it actually is. Biased results lead to inaccurate conclusions. Missing data will also reduce statistical power. Now, this is a funny one. Statistical power. Power is often the power to detect, correctly reject a null hypothesis, right? I've been freaked from this in a while. I've been Bayesian for a long time, so I've been like, whatever. Still matters, but in different terms. The funny thing about power is it's related to the accuracy of your parameters. And sometimes the author of the book talks about efficiency. We can quantify it better, right? When you fit a regression model, your regression slope, you get a point estimate. That's your slope. So if you can make predicted values, it's from there. You also get a standard error for that point estimate, right? Now that standard error is what I believe the author of the book is talking about is efficiency, right? So if we model, let's imagine we have missing data that's missing at random and we use maximum likelihood, right? If we could somehow see the complete data, the difference should be that our point estimates are roughly the same, but in the missing data case, we have fewer observations, right? And so if we handled it correctly, point estimate shouldn't have bias. The standard error will be larger with missing data than without. However, you saw, and we're going to talk about at the end of class, if you don't handle the missing data correctly, you'll have bias, so your point estimates won't be the same, but your standard error could be really small. And then some people would say, well, that's a really efficient estimator. But you can have bias on the standard error as well, is what I'm trying to say, right? And I don't know that concept comes across as well, but it does something to think about, right? If you think about it, if we make the missing data work the way it's supposed to, we should have less information than we have if we have a complete data set, right? The art of being wrong is really what we're talking about, right? We want to be wrong in ways that if we don't know what an answer is, we don't know. We say we don't know. And I think that's the key in missing data is we want those standard errors to be bigger if they should be bigger. It's a hard thing to think about, but it's really, I think, what drives what we're doing. All right. Questions on that? I think it matters. Of course, then again, you're enrolled in the class, so I should, like me telling, yeah, sure, of course, you must think it matters, otherwise you probably wouldn't enroll in the class, right? Okay, modern methods, maximum likelihood, estimates parameters directly from observed data, the observed data likelihood. So a model, we talked about linear regression. That model has implied distribution on one or more of the variables. Those distributions lead to a function that we then, when we pick parameters that maximize the value of that function. We'll discuss that much more in depth in 2 weeks, how that works. But that function comes from your model. Your model itself dictates what the distribution of your variables are. So a simple linear regression, y being predicted by x, your distribution would look at the normal distribution for y, because of the way it works out. We'll see that in a couple of weeks. And using the normal PDF, you'd build a likelihood function. That function would have the data in it, the residual variance in it, your model parameters in it, right? Those things the things that you don't know, you've observed the data, you don't know the model parameters. So what you're trying to do is pick the model parameters that maximize this likelihood function that you build from it. That process is the core of all methods that we do. When it comes to, it's the part you don't normally see in applied statistics courses. We sort of take methods as they are. But in this class, because the missing data can be in different variables. We may have to deal with a lot of methods all at once. So Bayesian estimation, turns out, is what you do in maximum likelihood. Although we don't maximize the likelihood often, we can. Bayesian is a lot of things. Bayesian is not equal to MCMC. Even though those of you who took my Bayesian classes, we always used MCMC. We could maximize a posterior distribution likelihood as well, right? But oftentimes we use Markov chain Monte Carlo. It doesn't maximize the likelihood. It sort of samples from a posterior distribution. And how we form that posterior distribution is taking our model data likelihood and adding prior distributions to our parameters and using Bayes difference. Right? We do that of likelihood function. But why Bayesian estimation works well with missing data is all because it has a likelihood function. So you're getting a trend here, right? Missing data needs a likelihood function. Why does it need a likelihood function? Because the likelihood function includes in it distributions of the variables that have missing values. And that means you can model them. You can talk about how likely those missing values happen to be. Right? Turns out, multiple imputation, it doesn't seem like it fits with the other two, but in the process in which it's usually implemented, and the one I'm going to talk about the most is missing multiple imputation by chained equations. There's a package called mice in R. It's kind of neat to use. You get a bunch of data sets. How do you handle them? So you get a bunch of imputed values, but the limit, sort of the process, breaks the analysis down into very small univariate models, but does so recursively, almost like every variable predicts each other. And that's how missing data gets filled in, completing a set of data. The limit of that process mathematically arrives at what we get with maximum likelihood in Bayesian as well. And so really, we have all three of these tools. Why we have all three of these tools, and what we're gonna dive into all three of them, like for the bulk of this class. Why we have all three of these is because some methods are easier to implement in some ways than others, right? So mentioned before, there's not a lot of easy ways to use maximum likelihood that's not the joint model approach. I'll put the joint model in quotes there for lack of a better term. Joint model meaning like a joint distribution of X and Y in a simple linear model. And actually, it's the factorized model is the hard part, right? You can have a model for Y given X and a model for X, and you can put them together simultaneously. But finding an optimizer to do that or finding a platform to do that can be difficult depending on the distribution of X or the distribution of Y. For instance, I'm going to show you Levon. Levon's fine until you get to categorical data, and then you can only have ordered categories. Well, what if you don't have ordered categories? You have nominal categories. Can't do Levon, right? So where would you turn? Probably in Bayesian or multiple imputation, right? So why all three of those is within one of those three, your solution will be found. It doesn't have to be the most complicated way to get it. You just have to understand the properties of why you'd build it. And that's what this class is about. Does that make sense? I know you read all this in the book. Is my commentary on this helping give it more depth and profile? I hope it's helping a little bit. That's my goal with this class. It's a little bit weird. Normally, hi, Kate. Normally, I teach a class with a lecture. I'm like, yeah, there's reading, and this is like the flip of it. So I'm not feeling like my normal self. So help me out here if I'm not giving you what you need. All right. So typically, and this is what you read about, and in chapter 2 and 3 you'll read a lot more. The word full information comes in, right? Because like everything, statistics is a big field, data science is a huge field, and the methods that we use got built in almost like in silos, right? So full information came out because in factor analysis and structural equation modeling, when we originally had the first versions of the software, Lizral, you didn't have to give it your data. You had to give it your covariance matrix of your data. You see the difference between the two, right? And based on assumptions of the model, the likelihood function took as input the covariance matrix. And yes, that's maximum likelihood. 100% maximum likelihood. However, that's not full information maximum likelihood. The difference being full information is the model itself is at the data, not a summary of the data. And there are different methods that you'll see here in the world, and we have to make that note. Basically, the likelihood function has to contain observations themselves, not summaries. What are summaries? Well, again, early days of structural equation modeling. I'm talking early 1970s through late 1990s, although M+ came along in that range, EQS. There are a number of other structural equation modeling software that, other than Lizrule, that handled full information. But if you look at Levon, if you switch to categorical data, it does not. It says maximum likelihood. It's not full information. What's it doing? It's calculating a tetraquark correlation matrix or polyquark correlation matrix if you have polytomous items, and then doing factor analysis on that matrix. Right? That's a summary. And now that means, technically, that summary, how did you compute that matrix? Because that is the thing that needs full information for. And most of our methods for calculating covariance matrices or polyquark correlation matrices have missing completely at random assumptions using pairwise or listwise deletion. Right? They don't have to. Some of you enterprising students could be like, hey, I want Levon to give me somewhat more full information. You can work on the part that gives you the tetraquark correlation. If you built a full information likelihood system there, it might help. You'd still have some bias that it would work. Anyway, the point I'm trying to make is, when I say maximum likelihood, it has to be a likelihood function where the observed and missing data variables are present, right? Not some summary. We good? All right. Okay. Then we get into the layers of what's missing and how it's missing, right? Missing data patterns versus missing data mechanisms. And missing data patterns, as you saw, are, is it better if I come out to the middle here? Is that better? I gotta remember, I'm not tethered to my machine here. I feel like I'm over in the corner. This is better. Like I need I'll get a clicker next. Anyway, missing data patterns, it's basically organizing your data to see where the missingness happens, right? And I'll have a slide that has a picture from the book to describe it. That doesn't describe why the data are missing. That doesn't tell you mathematical assumptions about the type of missing that you have. It's a statement of what's missing and what's not. And where that can become helpful in a limited sense is in the case where you want to take this joint distribution approach and factor it, right? By saying, for instance, if you're going to predict y in a regression with a variable x and a variable z, and x and z both have missing, right? Do you have patterns where x and z are missing simultaneously or not? Because that might change how you decide to model the work. So one way of modeling it would be saying the distribution of y conditional on x and z times the distribution of x and z together. That would be the case where if you wanted to worry about, if you had missing data on both x and z, you've built that. But if you don't, the distribution might look like distribution of y given x and z times the distribution of x times the distribution of z. Right? You may have a different way of building that, or the distribution of x given z, if only x has missing, something along those lines. So there are ways to think about how missing data patterns might help build a factorized analysis. But generally speaking, and this is my naive impression, in the work I've done, I haven't found them to be very useful. For most of what we'll do, at least when we assume missing at random, a mechanism called missing at random, that we'll talk about in just a moment, we can find a way to sort of avoid that, I think. Questions on patterns? Oh, we'll see those in just a little bit more. A missing data mechanism actually is the processes that describe the different ways in which the probability of missing values relate to your data. Now, this is a weird construct because to think about it, and in reading the book, for those of you who came to my office hours today, you'll hear me repeat myself, so I apologize for that. But think about it this way. When you plan your study, let's imagine you're going to collect a sample size of 1,000 people on 10 variables, right? And you're just going to have a 1,000 row by 10 column matrix. There's your data. Ta-da. What you have to think about is, okay, each one of those potential observations has a chance to be missing. This hypothetical probability of missing itself. And the missing data mechanism describes what that probability is dependent upon, right? And we can talk about it right now. We'll go into depth in just a minute. It's potentially observed data, potentially missing data. And then if you think about, we're modeling the probability of missing versus not, that's usually in some, if we could build a statistical model for that, that model itself would be some type of logistic regression, right? Modeling the outcome of a binary variable. So that model itself has model parameters, right? So if you had a set of observed variables or missing variables. Well, here's the hard part. The missing data you don't have, right? So how do you put that in the model? You don't. So where does this exercise lead us? It leads us to a hypothetical, like a thought experiment mathematically, which when I was in your seat, couldn't stand. Like I didn't like, oh great, we're going to hypotheticalize. But what it tells us though is it sort of outlines in which situations methods can mathematically accommodate missing data versus which ones they cannot, right? So these are more hypothetical circumstances. You'll note that most of these assumptions are untestable. I think the exception is missing completely at random. The missing completely at random test, I don't know anybody who ever uses it. I'm sure it is used here or there, but I don't, practically speaking, it usually is, not there. But these also, missing data mechanisms tells us what's assumed about the data itself as well too, right? So in summary, patterns are where there are holes in the data, whereas mechanisms, that's a LaTeX error there, describe why the values are missing themselves. Any questions on it? So patterns may help us with factorized analysis. Mechanisms sort of help us structure where things might go wrong if we use certain analyses, right? How are we doing? Yes, Farhan. Not necessarily, no. In fact, the way it's structured is it's going to be different potentially, right? Those model, the hard part is, again, these are hypothetical models. But let's imagine we could observe all the things that we'd put in it. Then you could envision us having for each variable like a prediction function. So all the observations in it would be dependent upon if we could have somehow observed the missing data or the observed variables. And each of those will have their own set of parameters, which in the textbook use the Greek letter phi, the circle with a line through it, to denote. Does that help? Okay. Other questions? Okay. So let's talk more about patterns. Nice picture, right? You can clearly see this. These are 6 of the patterns. I have to think there's more than that, but actually, no, general takes care of almost everything, right? There we go. I don't know about you. My data, when I do this, tend to come in like 2 patterns. There are actually 3. There's that one, general. There may be plan missingness. And then there's latent variable. I do a lot of survey research, latent variable modeling. And yeah, that last one's there. Plan missingness, this is me like saying, this is a common item form design here. We've got all the item, or one variable y that everybody gets, but only certain groups get different ones as well. It's like a linking design almost, right? So you'd see that as well. And then, but the general pattern, when I'm just collecting data, actually, what am I saying? Actually, no, that's not true. I do collect data, collect a lot of it. When I do collect data, this general pattern tends to be what's missing for me. It's all like scattered everywhere. But univariate patterns are really easy. I don't know. I think that's more like, let's get into, wade our way into where the world is. So univariate patterns, one variable missing data. How many of you have ever seen that in your data? Probably not. Monotone pattern, if you have a longitudinal study, the monotone pattern starts to look like that, where if Y1 is data collected at time 1, time 2, time 3, what you see is there's dropouts at time 3. Those dropouts don't come back at time 4, and then there's more dropouts at time 4. So this sort of monotone missing pattern. Again, most of our longitudinal, this is a gross oversimplification, as you might imagine. When you have a longitudinal study, it's seldom the case that you're just measuring one thing. So oftentimes, the dropout is the indicator of the full missingness, whereas of the people you did observe, you may end up getting something like a general pattern of missingness for that those data as well too, right? So the general pattern, again, to me, the nice thing is these methods, again, scattered randomly across the data set, no rhyme or reason. Somebody didn't answer this, somebody didn't answer that. And this is where the people who do the theoretical statistics say, yeah, that's why I do theoretical statistics. People don't ever cooperate with the data. And then that's the other side with, I'm like, I get it. We get asked for data how many times every day these days? Like, I can get why I don't want to give a lot of data. The nice thing about the general pattern is, again, maximum likelihood Bayesian estimation, multiple imputation work well for it most of the time, so long as it's general and not under-identified. But I'll talk about that in just a bit. And then this leads to not have, there's really no reason to choose one analytic method based on this missing data pattern, right? It's everywhere. And this to me is the most, at least for my data, this is the most common type. Planned missingness, I just mentioned before, variables are intentionally missing for a large proportion of respondents. In educational measurement, that's different forms of assessment, right? Happens a lot. Not bad. Now we have different ways of trying to put those forms onto a similar metric. We may have common items. I mentioned that about the graph before. Y is like a common item, but may not be in others. This idea has been ported to other parts of the world, but to me, it's, I think, probably been done in educational measurement since we've ever had assessments, right? Because you want to have multiple forms of a test for multiple reasons, right? And you have to sort of assume that those forms are on the same metrics and measuring the same deal. But yeah, planned missingness happens. The book makes a big deal of it. It's kind of funny because the editor of the book series, a guy named Todd Little, I used to work with him at Kansas, he liked a lot of planned missingness at the time. And I think that's part of the reason why it shows up in chapter 1. I think the reality of planned missingness is we do this all the time, at least in measurement context. And you can do that also in other contexts as well, too. You see it in longitudinal studies or other ways. So it's just part of what happens. It does say often with minimal impact on statistical power, and then chapter 1 goes into how to estimate that, with simulation and so forth. So I would say if you're in the middle of a planned missingness design, it helps to work overtime to determine the impact on power, because you can. You're basically saying, yeah, I don't need this information from these people. Depending on what you're trying to assess, that may be good or bad, right? In educational measurement, I talk about, we have planned missingness because we have multiple forms and assessments. That's understandable. Let's just take flat forms. I don't want to talk about multi-stage tests, and I want to talk about computerized adaptive tests, just a fixed form right now, right? Instead of fixed forms, it's planned missing. But our point of interest is the person, right? And so usually each person takes the same number of questions on a test, on a form, right? There may be 20 items on each form of a test. Maybe 5 of them are common across all forms, something along those lines, right? So our inferences still have the same amount of data for each person. So our missing design isn't really hurting us as much. I guess it would be if you thought, oh, I was going to give this person all the forms. If we have 3 forms, 20 items each, it'd be 60. So yes, we would have less precision about a person with 20 versus 60. But in some respects, if we're looking at the person, we still have equal numbers of items per person. So our precision will be roughly the same. It'll be less than 60, but that is part of what we think about. Alternatively, if we weren't interested in the person, and we're talking about maybe features of some item responses or group differences, that is where we start to worry about power a little bit more, right? We don't want to have a situation where, one group of people only gets one form because now we can't tell if it's a group difference or a form difference if we're looking at results, something along those lines. So, and not only that, power is impacted by that then too. So, plan missing designs are cool. They certainly alleviate the problem of overburdening your subjects, your examinees, your respondents with um, questions, but they take a lot of planning. Let's put it that way. If you roll out to Chat GPT and get a plan missing this design, you might want to have that looked over by a few people. Let's put it that way. It'll get you in the ballpark, though. Sound pretty good. All right. I keep ripping on Chat GPT. It's here, and I use it. It's fine. But we all know what it's not fine for, right? Okay. It's really good at taking my English and making it English. There. Latent variable pattern. Now, this to me is what I also mentioned last week, but I wanted to challenge you with. Anybody thought about what I said? There is no score, right? There is no score. If you think about it, it's sort of the difference between, like, let's take a sum score. There's always a way to sum up variables, and that is a score. But the properties of it only come from believing it represents a construct of our classical error model ideas, right? So if that's the case, then what we look at the sum score, those of you who've taken theory and technique, help me out with the sum score here. The expected value of the true score is equal to the sum score, right? In the limit as the test length goes to infinity. Am I wrong about that? Is that what I get? I don't believe I should have looked that up ahead of class. But anybody want to help me on that? Check me on that? Anyway, the point I'm trying to make is we put a model onto scores, and if that's the case, we're relying upon limiting distributions and so forth. The observed score is our best estimate for it, but that's only one estimate. And in the context of missing data, what we just talked about, and what the book talks about, and what we're going to talk about, is the worst methods for imputation are single imputation. But if you believe that score represents the expected value for an infinite test, that's a single imputation right there, right? So what I'm trying to say is, when you believe psychometric properties about adding up data, you are basically saying, I have no score. This is the best guess of the score for finite amounts of items that I have. And that's with the sum score. Let's not even get started on the latent variable, because the latent variable is not observed, and that's where the name latent comes in, right? So, anybody want to fight me? I love it. Let's not fight like altercation, but like a academic debate. Counterpoint? Anybody? I like it. It's okay. Challenge accepted. I don't know that I'm saying all the right things about the classical test theory, but I do believe I just need more specifics. I have the intuition that what I'm saying is appropriate. Anybody? So yeah, you get a test score, but what do you do with it? Right? How many of you have used test scores in analyses before? Right here. Anybody? How many have not? How many? No one. Who's not used a test score in an analysis before? Good. I'm sorry, you're in the. Sorry, we have to talk. I'm obligated to talk about it in our program, but I will get to the rest of the data. But this thing's kind of important, right? A test score, not just test score. It could be a survey, questionnaire, anything that represents a sum of Likert responses. Does that cover you? Okay, there we go. There we go. How many of you used just the score that you got in that analysis? I'll raise my hand. I did. Anybody else? Yeah? It's okay. This is like missing data anonymous, okay? Just this is where we do this. The problem with that we're going to map from missing data onto is that score represents our best guess from a distribution of scores. Sometimes that distribution is easy to see. Sometimes it takes a little bit of math, right? So what should we be doing? Well, in your analyses that use that score, a single imputation part is not advisable. Multiple imputation would work better. A simultaneous analysis would work out even better. Latent variable model for that. That's what structural equation modeling does in a broad sense. Still doesn't help us if we have missing data on the variables that go into the latent variable, right? The actual responses to questions. So scores are single imputations. That's what I'm going to say. So long as you believe psychometrically about it. So this is the hard part. The one catch is the sum score. We can always add variables together. It's what we believe about them once they're summed together, right? And if we start taking that classical true score model where that sum score is equal to true score plus error, that implies it's a single imputation. There. Weird, right? So I came in and said, all your analyses are wrong, and same with me too. But that's a key point. Okay, finally, the under-identified pattern. Interestingly, this is a fun one, right? Let me give you an example where it bites me. Under-identified, let's think of it this way. Let's imagine I have two test forms, Form X and Form Y. Form A and Form B. A and B, let's call it that, right? Okay. And I have a group of respondents and they only take one form, right? Half of them take Form X, half of them take Form Y. Different items in the holding. Let's even actually you can have, let's just call it completely different, non-overlapping items, right? So now back up. Let's have a set of common items. The 20 item test with 5 overlap, all right? Each person takes, all right. So if I want to run a correlation analysis on my 20 items, just a correlation matrix, what's that matrix going to look like? Now remember, I don't have 20 items. I have 20 items per form and 5 overlaps. So I have, 35 items, right? So if you look at my data matrix, the first 20 columns are Form A, and then from column 15 to column 35 is Form B. So my data matrix is like everybody, if I stacked it in a way where everybody took Form A, it'd have data for the first 20 rows for the first set of people, and then the last 20 rows for the second set, and there'll be an overlap on 5 rows. What's my correlation matrix going to look like when I output it? If I did not allow, if I didn't do listwise or pairwise, actually, if I didn't do listwise deletion, I only did pairwise deletion. Only the 5 items that were common would be able to have correlation because those items don't have any missing data, right? But if I wanted to look at the correlation between item 1 on Form A and the last item on Form B, I have no one in my data that took both. So I'm missing all the way on the first set for item 1, and then, I'm sorry, for item 35, complete data of item 1, and then it flips. There's no correlation. Guess where that provides the problem, right? It's an under-identified pattern in some cases because think about now, I know this is sort of mixing classes and some of you may have not taken this, but model fit methods often rely upon describing the patterns of correlations and covariances in your data, right? So you may not know all the model fit methods. If you don't, that's okay. But think of it this way. You're now describing model fit to that middle part of the correlation matrix, so only 5 items that have correlations. The other ones you don't have data on. You can't create a correlation. You can't even do model fit, right? So why I say that is, now I can run a model on this just fine. I can get point estimates for latent variables, but there's certain things I can't do when I have an under-identified pattern. How do I deal with that? Right? If you go into, those of you who've done multidimensional IRT, you know in R there's a multidimensional IRT package, MERT. They have what I like to look for model fit, this thing called M2. M2 looks at basically contingency tables, 2-way tables, 1-way tables with your data. Contingency table is what we draw correlations from. So that correlation is in the middle of that, right? So when you get to use M2 and you have some block design like I just described for your forms, it will not give you model fit. But guess what it will do? It'll be like, hey, would you like to impute the data? And you can. And you can impute it multiple times and get an average model fit. But guess what? How it's imputing the data? Based on the model. So the imputed data based on the model tend to look like the model. So guess what model fit gets? It's good. So if ever you want to cheat and get model fit to be good, make a plan missing design that's somewhat under-identified to check for model fit and impute the data based on the model, voila. No, that's not actually scientifically valid. It's more one thing that we have to worry about. And that's actually what we're building towards this here as well. The idea for missing data is the mechanism, if we're going to rely upon imputation, it has to be model agnostic. Because if we start to favor a model, our data that we're imputing will look like the model we're using. And that's not why we're doing the science in the first place, right? So, all right. Any questions on any of this? Yes, Vladimir. Okay, so the pattern, the way I understood the writing of the author, is that we never observed Y4 at all. So what we have to do is infer it from a model based on the three variables we did observe. Now, what we typically do in psychometric models, so if let's imagine these three variables are continuous and we put together a factor analysis, this confirmatory factor model with three items, it's just identified it works. There are methods to estimate what this needs to be. There are methods to estimate what its distribution is, for lack of a better term. I can tell you methods I like use Bayes' theorem. You can get a Bayesian estimate of it, but you don't have to use a Bayesian. You can always use other estimates as well too. Does that make sense? Yes. All right. Other questions? Yeah, another one. It's a bit of both. Take a look at variables 3 and 4 here. Is it about, so if I wanted, it's hard to tell based on this design. Let me see if I can get this a little bigger here. There we go. Much better. All right. So if we say that variable 4 is missing in all the cases that variable 3 is, and then variable 3 is missing in all the cases that variable 4 is, although it's not exactly drawn to that scale, but let's say it is. If that was just from design, like a plan missingness, we won't be able to estimate the correlation between 3 and 4 directly. We'd have to maybe find another method to do it, right? So that's why it's under-identified. So, but it does relate to amount in that, like, if this is not true, if there really is a few observations here that have 3 and 4 and a few observations here that have 3 or 4, now we can estimate a correlation with a really large standard error, right, in theory. So in part it's amount, but really it's about an amount of overlap between variables, right? If you look at a contingency table that has, like, if you were to go and recode this from the numeric scores and make each of these whether they were missing and whether they were not, and you put a contingency table together, if that contingency table doesn't have certain cells, right, that's where it's under-identified. Does that make sense? You're welcome. Under-identified in general, I use that term to refer to statistical models that will break, that will not give you output, even though the model mathematically should. So why it breaks is the data, right? The data, sometimes I call this empirically under-identified, meaning I don't have data to support the model that I'm trying to run. Does that sound good? Okay. All right, at that note, it's time for our first break. You want to take 10 minutes? Stretch your legs. I'm going to grab some more water. Anybody have questions or want to talk? I'll be back in just a couple minutes. So I'll pause the recording too. Yeah, there we go. All right. So, any other questions on patterns of missingness? Okay. So, again, big picture for patterns of missingness. For right now, the general pattern is probably pervasive in what we're going to do. with the exception of some of the antiquated methods that showed up at the end of chapter 1, which I'll cover a little bit, like carry forward designs and so forth. So even though a lot is made about patterns, and I always felt like we talk about patterns a lot, practically speaking, at least in the way I've had to worry about missing data, I haven't seen it to be that big of a thing, but that doesn't mean it's not going to be in your context when you have missing data. Let's talk about missing data mechanisms. All right, so again, missing data mechanisms, it's a hypothetical, it's a thought exercise, right? It's basically trying to denote mathematically what could be the cause of missing data, and then if we carry that forward through building a likelihood function, we see some mathematical results that sort of allow us to believe, for instance, that missing at random works well. If that's the mechanism, maximum likelihood will work well for it, right? So it's more on the hypothetical side, mathematical side, but it does structure how thinking goes, generally speaking. So we're going to dive into each of these three. I know you've talked about, I know you answered questions about these. We'll dive into them, but then the moral of the story boils down to, like, it's like Goldilocks and Three Bears, right? There's like missing completely at random that's never going to be in data, right? so you're like, well, how much missing at random do I have? All right, well, I need to use maximum likelihood. That's a good idea. Likelihood-based methods or missing in multiple imputations. So you start doing that, assuming missing at random. But if it's missing not at random, well, good luck. You got to do a lot more study, right? You sort of have to be clairvoyant or know about the problem that you're studying very well. That's what it's going to boil down to. So what that really means is, hey, missing at random, let's protect ourselves from that. And then when you get to missing not at random, you have to really work hard at it. But we'll cover the logic of each of these because it sets up the mathematics behind it, right? So here is a hypothetical. Here's a real data matrix. This is the observed data. And so we have some data here, like person one's third response is missing. We could basically put all this, each one, if we looked at each of these as sort of a vector, we could put them into a big matrix, and that's what Y observed is. It's what's actually in our data, right? And then really, here's where the hypothetical comes from. To do this exercise, we have to observe, kind of believe that, yeah, there actually is complete data. We just didn't happen to access it, right? For whatever reason. So this complete data, sometimes denoted as Y1, sometimes YCOM for Y complete, that is what we're after, right? That's the ideal. This is what we get, right? So the fact that you see 15 here, there's no one alive that's going to tell that to you, right? This is where the hypothetical comes from, right? We have no idea what this is, but the hypothetical says it does exist. It was 15, and what we ended up with was something like this. So our method has to think, well, we don't know what that is, but we have at least some guesses as to what it might be, right? Some plausible ideas, plausible values. And then there's the missing data, right? If you were to invert Y observed, you'd have the values we would have seen, like the 15 in that spot. However, that is, and again, you'll never have this, right? Y miss, you never know what those are. But we need to denote it because it helps distinguish what happens. So Y miss is basically if we took Y observed and added Y miss to it, and wherever there was missing, we just made it 0, we would end up with Y complete, right? But remember, we don't get when there's a real data set, we don't know what that is. We can do this in simulation, but in real data, we'll never know what the missing values are, right? So right away, you should realize this is the hypothetical because we're never going to figure that out. All right. So Rubin's framework models are basically, they explain whether a participant has missing values, right? So here, if we were to come up with, for each variable, an indicator of whether we observed it or it was missing in our complete data, YCOM, right? Not YCOM, YOBS, excuse me. So in YOBS, that's a binary indicator, right? And this thing is just an indicator of what is there or not, right? And so we can talk about M being maybe a set of 3 vectors, right? So it's like a matrix itself. So here's some example data. I have IQ scores and job performance. Actually, these data, I believe, were from his first edition of the book, which are no longer in his book, I feel like. I may be wrong about that, but I think it was in the first edition. Anyway, I gave examples with this. I used these data before. I'm going to use this to make it a little bit different from the examples you saw in the book as well, too. So here, let's think of it this way. We have some IQ score. Don't get me started on IQ scores. I firmly believe, look, my research is in multidimensional measurement models. Intelligence is multidimensional, so one score that captures it all is somewhat illogical. But let's pretend, since we're in the hypothetical example world, let's pretend that this measure of some type of intelligence, cognitive ability, IQ, is related to some measure of job performance. That's what this is. Okay? And if we could observe all the complete data, this is what we would have. All right? Sound good? Again, I don't believe in. I believe in IQ. Let's put it this way: this Montessori, my idea of multiple intelligences. That's me. I like that. Right? There's no one intelligence. I try to tell that my son's like, oh, you misses the problem. Oh, I'm not smart. No. Not that you're not smart. That problem was hard for you. So no big deal. It's nothing to do with smart, right? Anyway, but use this for missing data mechanisms. We've got MCAR missing completely at random, MAR missing at random, and MNAR missing not at random. And if you start talking like that elsewhere, people think you're crazy. MCAR, MNAR, MAR, right? It is sounds kind of weird, but forgive me for sounding crazy in class. Should we just agree it's probably better to say MCAR than MCAR? Or do you have a preference? Can I call it MCAR? Just, I'm acknowledging the crazy. MNAR. I can do that. MNAR. I like that. I like that better. That makes it sound much more like elegant, right? When really that's the really bad one, right? That's not good. All right. Missing completely at random. The data are missing completely at random if the events that led to missingness are independent of the observed variables and the unobserved parameters of interest. Actually, the missing variables as well too. Where are examples of MCAR? Good luck. All right. I'll give you one. You have an online survey. It's on Qualtrics, and somehow Qualtrics throws a server error halfway through on someone's server, on someone's data. You know what I'm talking about? Yeah, item 10545 503 error. They're going to be missing data, right? Missing completely at random? Probably. That person just happened to be at the time that the server had an error. I'm saying an error, not planned maintenance. Let's hope they don't have planned maintenance for the entire system at some hour of the day that's related to someone who really needs to answer that question. You can see what I'm saying with this, right? Getting on auxiliary variables, to hour of day, things like that. Another way of thinking it, it's literally a coin flip that happened that caused the missingness, right? I can call it a coin flip that's 50-50. It may not be that percentage, but a random number that causes, right? Some chance event. Or planned missingness, right? If I mentioned this multiple forms idea, Form A, Form B, if you're collecting 1,000 people and you randomly assign the first 500 to one form, the second 500 to the other, I believe we sometimes call that an assumption of randomly equivalent groups. But that random process, MCAR, right? Have it. Anybody else have any good examples of missing completely at random? I can't say the dog ate my homework. That's probably not going to work. Your sister ate your homework? I'm sorry. What's that? There you have it. But what's that? I believe that. So in that case, is that completely at random? Because if there was a group of students and that dog was more prone to eating homework, that species of dog, let's tell it that way, that would be an auxiliary variable of whether or not you had that species of dog at your house, which may not be missing completely. But that's twisting myself to get there. So I guess my purpose in doing this is seeing if you guys do examples and I'd see if I could twist it around where it wasn't.
So then using that same logic.
Yeah.
So you said earlier
Yeah.
here. What if it's the type of computer or the server itself that's doing it?
That's it. That's what I'm saying. Like if the server went to planned maintenance at 7 in the morning, and this questionnaire was talking about, like, I don't know, conscientiousness, or I don't know, some type of something that was related to someone needing to do work at 7 a.m. that was like cognitive work, right? Which a lot of people do. I'm not one of them, but a lot of people do, right? That would affect. So yeah, that would be not necessarily completely random, right? Database, but then, and like you said, okay, what about the server? What about, okay? So now let's imagine you're asking, the survey is about like, poverty or living in poverty, and you're on, whatever you can afford, which is usually not very reliable, right? That thing would also then potentially be related, no longer missing completely at random if the computer glitch, because the computer glitch was related to the part that you're trying to measure, right? So, so what I'm trying to say is, it may seem benign. Oh, it was an error, but it's likely potentially not. And there's many different ways in which that could be, like, missing completely at random sounds like it's implausible, right? You literally would have to be like, you really angered your undergraduate research assistants in your lab, and they went through an R and used the RUnif function, and if the result of RUnif was less than 0.2, it deleted the case or deleted an observation. That's missing completely at random. But then again, just kidding, right? But I'm just going to try to, like, what you can say. So what I'm sort of arguing here, which is a controversial topic, sort of. I mean, as statistics goes, right? Is it really completely at random if you don't make that as part of your sampling design of your study? And even then, as we know, with the finite sample, you need sample size for that to be roughly random and equivalent as well too, right? Anybody want to? Any other good missing completely at random thoughts? Yeah, Vladimir. Yeah. Missing observations. So sometimes I think I'm probably commingling if you're talking about how I spoke. Um, I think I need to be a little more precise. A missing observation is like this omitted response here. Some people might say, if this were flat lines, you omitted everything. And I'm saying observation and data synonymously. So I think I'm saying it to be the same thing. Whereas what I'm saying when I say a missing observation or a piece of missing data, it'd be, does one outcome for a given person, is that missing or not? Does that help? Rather than a set. No, probably not. Well, if they give us nothing. So let me back up. We haven't talked about it. The homework's about it. Actually, I mentioned it. If you collect, let's imagine Y1, Y2, Y3, these are your study variables here, right? And you have a person that gave you none of them, but you collected demographic information, right? Now, I didn't show that up here, but that person's demographic information, they're male, young, don't care, undergraduate, name it, right? We could potentially use that auxiliary variables in a model as auxiliary variables and then try to use their data, but they don't have any data, right? Having no data means they would be treated the same as everybody who gave us no data that had the same auxiliary variable scores, in a sense. And that's probably illogical as well too. So we got to have at least, like, we got to be like this person here that has an 8 and nothing else, because that at least starts to make a little bit more precision toward what we're doing. If you want a rough guiding principle, think of it this way. So when we get to chained equations, it's kind of silly, but it works, right? And it's this. I'm going to initially start, and I'm going to say, I'm going to predict Y1 for each of the missing scores. What I'm going to do is I'm going to fit a model where Y1 is predicted by Y2 and Y3 in a linear regression, right? Multiple linear regression, just main effects. Okay? So now I can come up with a predicted value for each of these, right? And I will impute that predicted value with error from the prediction interval itself. And then you remember back in linear regression, the standard error prediction, had like a 1 in the denominator that was, or the numerator that wasn't there for the standard error, the mean. Anyway, you're going to impute those with error. So that's y1. Then we're going to go to y2, and we're going to model it as a function of y1 and y3. Same process. And we're going to go to y3 and do the same thing. So when we have no data for a person, there's nothing that anchors that process, right? That process I just laid out for you is the chained equations approach to missing multiple imputation. It has some mathematical properties that are nice that makes it look like some of the joint models. But with an 8 here, right, we have a better sense of what we can, our prediction interval for this person will be much, much smaller than if we had nothing there. And all the people who have nothing there, their prediction interval, if it were just these three variables, we'd have no way of predicting what they have, right? It would basically be anything. So that's where that can't happen. If there's auxiliary variables, we could build chained equations with the auxiliary variables in, and then we're able to predict as well too. But I hope that helps a little.
Yes.
Yeah. Other questions or thoughts? All right. Missing completely at random. I was arguing, probably not going to happen. Anybody? Let's just be real about it, right? But if it does happen, actually, here's our formal definition. The probability of missing, remember that's that indicator. If we were to build a logistic regression for each variable and model the probability of it missing, what we would see if we could model it, if we could take our observed data matrix as predictors, our missing data matrix as predictors, and then phi the parameters, what we would see is that this would have zero weight coefficients on observed and missing. Or another way of putting it, it would be like we could say they're not involved in prediction at all. The only thing that determines whether someone's missing are the parameters, and in that case, it'd be like an intercept, right? The intercept in a logistic regression roughly describes the probability of the log odds of the probability that somebody is missing. That's the only thing that does it. So that's the coin flip for you, right? The level of uncertainty, the amount of, the coin flip is like a 50-50, that intercepts 0 on the logit scale, but you can back map a certain probability of missing for it. So that's missing completely at random. And you can start to see why this thought experiment comes through. If you've read like statistical literature and you start to see functions being built, when we can reduce a function from this to the one in pink, it becomes simpler, right? It becomes easier. You can see how likelihoods would be built off of it. Effectively, the likelihood itself would not be conditional on something we didn't observe. So therefore, mathematically, this is giving us a basis to say missing completely at random, as implausible it is to have that data, will not hurt your model parameters. And why I say hurt there, I should have defined it a little bit better. There's an implicit idea. Remember in multiple regression, what happens if you do not include a variable that's needed in your analysis? Right? If y is predicted by x and z, but for whatever reason you leave z out, what happens to the slope of x if x and z are related? It changes when you put z in, right? That's what's happening here, right? Our observed and our missing, when we take them out of being conditioned upon, it's like saying if we needed them there, right? If this were truly it right here, but we didn't have it, a la missing, right? It would be a missing variable problem. Almost, it would be analogous to a missing variable problem in a linear model, which meant bad things happen to the rest of your parameter estimates if you didn't include it. Well, it turns out we can't include this because we wouldn't have no idea what y miss happens to be, right? So that's the mathematical basis for why these things show up. For Hunt. Yeah, so think of it this way. If we just take one of these missing indicators right here, just take one. We model that with a logistic regression. But the logistic regression only includes phi, which is the coefficients of that regression. Well, it's not really a logistic regression anymore. There's an intercept to it. Right? The linear model part of it would be that the missing data is being predicted just by the intercept because there's nothing else predicting, right? And so because of that, that's where phi comes in. That intercept then only describes the probability of missing once we convert it from logit back to probability. Does that help? Any other good question? Any other questions? I try to do my best to respect every question. I want you to ask. I say that because I'm imperfect, but at the same time, actually, I think you can, I think so. My teaching evaluation said I have tried to have respect for you. So please ask questions. No questions too small, no questions too, well, there are too big of questions. But anyway. Okay, what are the implications of missing completely at random? As I started to sketch out logically, this right here is what we're working with data, meaning whether or not something's missing is independent of what's observed or what's missing. So we should see that our methods do not give us bias to our parameter estimates, right? Our methods should work fine. That includes listwise deletion, right? Listwise deletion meaning if we're predicting y with x and z, and either x or z or both of them are missing, the whole case is removed. Well, what happens in listwise deletion then? Our sample size gets smaller, right? Sample size gets smaller. We would expect less efficiency. Our standard error should be wider, but our parameter estimates will be where they need to be, and there will be no systematic bias under or over on your standard errors as well, right? So missing completely at random mathematically does not pose a problem to the data. But again, how do you tell something's missing completely at random? Now, actually, we do have a test for this, but you get enough sample size, that hypothesis test is always going to say it's not true, right? So really, we need like effect size measures and stuff like that, which we could derive. But anyway, okay, are we good on missing completely at random? And actually, wanted to show, I didn't talk about this in the lecture, but if I were to show you these path diagrams, I'm not the directed acyclic graphs. I found these to be a little bit hard to sort of understand. So y star here is y observed, right? Y is the incomplete data, and then M is the missing indicator, right? So a directed acyclic graph, if you're trying to read this, it'd be like saying that the following, that the realized value of y itself has something to do with data, something to do with the missing data, but because the missing data itself is not a function of y directly or x, it's sort of, once we condition on what we have, it's sort of independence happens. So the directed acyclic graph, if you're into that type of idea, it works. I struggle with it because graphs aren't models, and I'm stuck in model parameter. Like for instance, this is a binary variable, m is a binary variable, x is continuous, y is continuous. Like, so the graph is not isomorphic with link functions or parameters or intercepts or all that stuff in this context. So I don't know. Maybe you found these graphs useful. I didn't find them super useful or informative, but I did want to mention that. Any questions on the graph? No. Okay. So here is missing completely at random data. Here you'll see, regardless of your level of IQ, you may have a missing value in our data. And you could think about people with missing data here could be employees that didn't get hired, right? So if this is a job performance task and you didn't get hired for the job, your data are missing. It's kind of like, a lot of undergraduate institutions want to evaluate how like ACT predicts first year GPA. One of the problems is the students who didn't go to school there, or the students who didn't get admitted to school there, have missing data, right? So it's part of a problem. But here you'll see that low IQ scores have missing data, high IQ scores have missing data. It's almost as if they didn't collect IQ to interview people for the job, and that would be consistent with most of the jobs I've ever worked in. Although I guess they want me to have a PhD, so that's not really IQ. Let's be real, right? Those of you, I remember being in one of my first classes as a TA in grad school, and I was TAing, and there was a different person teaching, and one of the students asked, like, just a random question, when did you know you wanted to get a PhD? And he's like, well, when I was a grad student, and I saw what working with professors was like, and I'm like, oh, yeah, they're not perfect. Many of them aren't high IQ, right? Multiple intelligences. So PhD is determination. It's not necessarily, having academic ability helps, but determination matters the most, right? Anyway, that's how I admit students when I admit students to work with. I don't know why I put an MAR data there. Okay, but here I can show you. Here's our complete data example here. I estimated this using maximum likelihood in Lavon, and I'm going to teach you how to do that in the next couple of weeks. And as I did this, as I'm building this, I'm like, no, I need to teach you Lavon. Otherwise, we're just going to sit here and go, well, I don't know how to analyze the data. Here you'll see the complete data right here. This should actually be MCAR data. I think I made a typo here. This should be MCAR data right here. Yeah. So let me just quickly show this. This should ignore MAR. That's me dropping a C. That should be MCAR. These estimates with complete data should be our gold standard, but remember, this is a sample of data that probably were simulated. So there are true values here, but what we want to do is see that what we're doing to data doesn't systematically or grossly change these numbers a whole lot, right? That's what we're looking at. So here, how do you read this? That'll be something we talk about forward. This is a covariance. So the model that I estimated here was not a real fancy model. I didn't predict job performance from IQ. I could have, but I didn't, because the job performance from IQ, that model would need a chained equation to work out in maximum likelihood when I get missing data. Otherwise, some of my observations will go away. I'll have listwise deletion. So instead, what I did was I said, I'm going to model them as a multivariate normal distribution, bivariate, right? So I'm going to estimate a mean for IQ, a mean for performance. I'm going to estimate a variance for IQ, a variance for performance, and I'm going to estimate their covariance. And anytime that you have a covariance along with a variance or standard deviation, you can convert covariance to correlation. That correlation, it's hard to read on here. That's this last value, 0.542 right there. That's their correlation. So when I estimate this, now, why I do that? This is equivalent, believe it or not, to having a model where I'm modeling both X and Y in the likelihood. So I would have Y given X as one distribution, that's our linear regression. I would have X by itself marginally, that's a different distribution. I have to pool them together. That gives us a multivariate normal. There's this weird, not weird, but nice. If you go to Wikipedia for multivariate normal, you'll see a relationship to linear regression. We're leveraging that relationship, right? So this should be what happens. This is our complete data model. If I estimate that model with our incomplete data that is generated by missing completely at random, you'll see that my estimates are roughly the same, not entirely the same. I really underestimate the variance for IQ, a little overestimate of the job performance of variance. The mean estimates are right about the same, right? So not too bad, right? Which is what we would expect. If I look at the standard errors, those things get a little bit wobbly, but remember, these data are 20 observations. So this is probably why Craig dropped this from his book. Hard to make inferences on 20 cases, right? But just to kind of get the sense. Questions on any of this? No. All right, let's move on to missing at random. All right, the formal definition of missing at random is that data, this missingness indicator, is a function of your observed data, what you have collected, and the missing data model parameters. Again, these model parameters won't exist, but they govern what the rate of missing would be if there was a hypothetical model we could run. But why observed? These are all the things we collected about a person, which could also be demographic information, auxiliary variables, things that are out there. So what we're saying is, the probability of being missing is dependent only on some or all of the observations that we already have and nothing else. It's a little bit weaker assumption than before. You can tell that there's more that we're conditioning on. So that's, actually I should say stronger assumption. Takes more data to solve. Come on, template. But what does that actually indicate? So that means why someone is missing an item or a question, giving you data, is not related to something you didn't collect, right? So that's part of what we have here. So here's an example. Let's imagine that this company did use IQ as a screening variable. So nobody who was hired with an IQ less than 90 got a job, and therefore their data were missing. Right? That's an example of missing at random because the criteria for admitting a person is in our data. If IQ is less than 90, they're missing. Well, we collected IQ. We even collected IQ on the people who didn't get the job at the place. And they may have been job applicants. They may have applied for the job. They may have somehow given you data to give an IQ score for. So that, to me, is what happens, right? So this is an example of missing at random. It's a very naive example, but it's what you think. So questions on that? Does that make sense? A little bit, maybe? Yeah. You're in trouble. I'm just. You have to put, so in short, why I say you're in trouble, you have to have a model for every variable that has missing data of some sort. So what do I mean by model, right? And we're going to have this in the next 2 to 3 weeks. We're going to talk more about what that means. So next week we're going to talk about the nuts and bolts of distributions and likelihoods. I have to do it to get us to maximum likelihood. When we get to maximum likelihood, what you're going to see is the likelihood function has to be a function of variables with missing in it. So X, the job performance, or if we miss on IQ, then IQ needs to be in our model data likelihood for maximum likelihood to hold, right? There are ways of doing it. So for instance, what I showed, the results here, this is MAR data right here. These results, why I specify this as a bivariate normal distribution and not X predicting Y, is because in a bivariate normal distribution, both X and Y are in the likelihood function. But when X predicts Y, depending on the software you're using, if you're using LM, X is not in a, it's not a function of X at all. X is a constant. It's no X, no data, right? So the answer to that is if we have missing observations in X, either it has to be in the likelihood. Well, that presents a challenge. I'm going to teach you how to try to build likelihoods with it in there. And so that's going to take some building blocks. It's challenging. Alternatively, chained equations, imputation. So what you end up doing is you start making a number of data sets where the data are imputed, if you can. Now, again, if you have unidentifiable missing pattern, the chained equations may start to fail in some cases. Not all, but some. Does that help answer your question? Yeah, so long story short, it's really simple when Y is missing. It's not as simple when X is missing. So your options are don't ever let X be missing, clearly, right? Fight with figuring out a model that assumes X, or multiple imputation. Multiple imputation will help you. Now, multiple imputation has another problem in that if we're going to impute 100 data sets or 1,000 data sets, how do we analyze those 1,000 data sets? So that comes out next too. So we'll get there. Other questions about that? No. All right. What are the implications? If your data are missing at random, and you don't use maximum likelihood. I should have made that in my comma there. So the first bullet, if missing at random is truly the cause of why your data are missing, and you're using some deletion method or some of the single imputation methods, you're going to get bias. You probably will have biased results, right? Think about this linear regression here. It's truncated because there's nobody below 90 that has a performance score, right? So what we may end up seeing is that the regression might not be as steep, predicting performance by IQ, right? It's truncated, attenuated, sometimes we call it, right? That is a classic problem um, in the measurement world for validity studies, right? Where we take an outcome of a score, singly impute a score, remember that, single imputation outcome, and then correlate it. Like, what's the correlation between ACT and first year GPA? I'm pretty sure whatever uh, is reported by ACT, likely singly imputed and truncated. In classic statistics, there are, like for correlations, there are correction formula, like Spearman create a correction for attenuation, right? So people have been aware of this for hundreds of years, not longer. Um, but our approach will be slightly different. We're trying to disattenuate it by doing something with the data that are missed. So bias results if you're using methods that are not maximum likelihood, that are not likelihood based. I'll put it that way. Clearly, you have fewer data points. So if you were to compare the complete data, hypothetical complete data results, to your missing at random data's results, the standard errors for your complete data should be smaller. There's more data to it, right? More data usually means more precision. And then inferences based on maximum likelihood will be unbiased. So maximum likelihood helps, or likelihood-based methods helps, but inefficient, meaning the standard errors are larger, just reflecting the fact that you didn't have as many observations in total. So missing at random, we can do something about. And that's why, like, the bulk of the textbook is built on it. And that's where, to me, as I mentioned before, like this is like whatever, I don't remember the Goldilocks story that much, but what's the just right? This is the just right version of missing data, right? Because missing completely at random, yeah, that's probably never going to happen, or seldom. Missing not at random is really hard. And this you can handle. So my goal in this class is to give you all the methods for handling and treating your data like it's missing at random. It's better than missing completely at random, but it's not missing not at random. Yes.
So the data that we're going to have, or data sets that are missing, are going to be.
Actually, we can't say that. But what we can say is what the easiest set of methods to implement are ones that solve missing at random. So we'll never know if our data are truly any of these. But what we can do is take steps to make our analyses more resilient in case they happen. Does that help? So it's on the flip. Like, we're going to diagnose, and if it's this, use this. If it's in practical reality, we have no idea, right? My hunch is it's probably somewhere between missing at random and missing not at random. But the methods that we implement, likelihood-based methods or multiple imputation, I think you could be doing with your data analyses as they are, and that gives you a stronger set of results than if it were just list-wise deletion. That's the thought. Good question. Other questions? Okay, moving on. So yeah, bulk of the book on this, bulk of the topics on this. We'll go forward. Let's take a look at comparison of results. Sorry for the font size. Make this a little bit different. Okay, 19.5 in complete data, 19.489 in the maximum likelihood. That's pretty good, right? Our variance is, again, shrunken a little bit so that causes our correlation to be a little bit different. And our mean estimates are getting closer, a little bit there. But again, not a great example with it, but something to look at, right? And so this method, this missing at random, or the analyses I'm showing you here, these are missing at random data resilient. How's that sound? If your data are missing at random, they're the ones to do. They're likelihood based. Right? Okay. What I should have done, yeah. No, not necessarily. Yeah, there's no way you can really get around it. Now, I say not necessarily. Multiple imputation, how you implement it, because you can actually implement that using likelihood-based methods or Bayesian, right? Let me just put it this way: in Bayesian methods, you can get smaller. The standard error here is equivalent to the posterior standard deviation, right? So how spread out your posterior distribution is for each parameter, and what you can do there is effectively make a more informative prior, and your posterior distributions will shrink. That technically is more efficient, but is that a legitimate efficiency, right? Or is that you can always, Bayesian's great because you can always make up data, right? If you think of in the limit, your priors that you set, you put super informative priors on your model, you don't even need data, right? You know what your parameters are. So that's the trade-off. So I think from an empirical science perspective, I would say that the only methods that you can sort of get reduced standard errors, but that's usually just a quirk of prior distributions. Mm-hmm. MAR sounds good. Yeah. Yeah. That's it. That's it. Yep. And missing data will, and then again, bigger standard errors means less power. So if you're doing a power analysis, you've got to sort of factor that in as well, too. How much of your data will be missing. What I really should have done here for the comparison is MCAR versus MAR. You can probably go back to the slides and see that. But no, actually, what I should have done was taken our missing at random data and run it through a model that didn't have X in it to show you the bias that would have happened. If you take the MAR data, if you take this data right here and use LM on it, you should see a difference. You want me to do that? I got time. You want to see it? What happens? Here I am again, promising a live class. Look out. This is going to go fun. This is going to be fun. All right, let's see if I can do it right here. If I do LM summary of LM, in this case, it will be perf C tilde IQ data equals job perf complete. That is this is what happens with our complete data using simple linear regression. All right. Now, if I take the same line and I change this to job perf MCAR, yes, perf C is not there, it's perf MCAR. Do that. Now, here's what happens. Okay, so perf MCAR, our intercept changes quite a bit. Our point estimate of the slope, 0.16 versus 0.10, those are pretty close. So not too terrible. But now let's see what happens when we take missing at random. Now, missing at random, our slope's still pretty close. The standard error is 0.05, 0.05, and 0.03. Bigger standard error. Yeah, it's not really showing it. So not a whole lot to show there. Again, I think I'm uncovering why this data set didn't persist. But at least it gives a decent idea of what MAR is. They just didn't take people into the job. Other questions on this? All right, got 2 minutes before break. Let me throw in a couple more slides. The missing not at random, very bad, right? Your probability of missing is conditional upon what you've seen, what you've observed, what you haven't seen, and then those missing indicator model parameters. The problem here is you don't have this in your data. So you can't really easily get out of this without lots of knowledge of what you're studying. This is often called non-ignorable missingness. That was another topic in the textbook. That means even if you're using maximum likelihood Bayesian multiple imputation, it's still going to negatively impact your results. The bias potentially, inefficiencies, your standard errors may be off even. The way I've seen this handled, I haven't, full disclosure, haven't read chapter 9 yet, working my way there. I'm going to see what those methods are. But in my practice, make it sound like I'm like practicing yoga, practicing statistics, practicing law. That sounds better. Law, my practice. I would say that I've seen people come up with models for the missing data that are based on theory, hopefully evidence-based theory, saying why it's missing, right? In the case of the polling error example, the thought was, at least the hunch in 2016 was that, when we sample people's opinion research, we often have to do a weighted variable analysis so that the people who are in our data aren't necessarily representative of the population at large. And some of the variables that we can't collect in opinion research about voting is whether or not a person is going to go and actually vote, right? And so in 2016, I believe the story is the people who what I've read about it is that it's usually white men without college degrees were not sufficiently sampled well enough, and they were thought to be low propensity voters, meaning people that wouldn't turn out to vote usually. But the latter part wasn't true, and so then what happened to happen is you had to adjust your voter turnout portion of this model to accommodate for those, because you can't actually observe whether or not a person is going to go or not to vote. That may be what I believe what's happened. I'm not a political scientist, but that's when I was reading about it, that statistically that was it. So that last part, the voter turnout model, is a model that tries to come up with data for missing. I see a question. I'm not familiar with it. Could you help describe it to me? Oh, possibly. That also could happen. Yeah. Yeah, actually, I feel like 2020 was a little bit of that way, where there might have been people saying they're going to vote for him, but then they vote for the other guy. Yes, and that also could happen, and that would be another sort of like in your turnout model, or in your, so now you'd have to come up with another component to the model that talked about whether the person who's giving you that response is actually truthful, in addition to voting, right? So yeah, yeah, that's right. So, but this is why we say it's not at random. There's a good reason this data are missing. Either a person doesn't want to answer the phone, doesn't want to tell you the truth, doesn't even know if they're going to vote. A lot of people who are low propensity voters probably don't even know they're going to vote up until the time it's going to vote, right? I mean, that's, oh yeah, I guess I should vote today, something along those lines, right? Not that we don't all get inundated by messaging and all this other stuff, but there are people who turn that off, right? So from a missing not at random perspective, all of the methods that we're going to learn for the bulk of the class aren't going to help us there, because it's still, we didn't collect the data to know whether or not truthfully someone will tell you the right response, or someone who will be actually going to the polls. So it's a complicated, almost intractable problem. Yet we still have polling organizations, right? And people are still trying to do this. So there are people whose lives depend on this who are trying to come up with a solution for it. But here I am. I was going to take a few minutes. I ran into break, but we can come back after break and talk a little bit more about this. Does that sound all right? About 10 minutes again? Sorry to keep you 3 minutes late. I hate being late to break, but this was kind of fun talking about break. Back again. Let's see. So yeah, missing not at random. Really, really difficult to get out of. Pointed out in the picture for the directive acyclic graph, that actually should be an N there, a little bit of a typo. So that happens. I did mention the directed acyclic graph before, but you can see that the missing indicator is dependent on what you observed. That's what X is there, right? But not what you're missing. And that is where in MNAR, the directed acyclic graph has this both missing and observed. So that's part of the reason where that's another way of looking at it. It's just the graphs are some ways that people think about it now. Maybe you think about it that way. I've always struggled with them. Used to like to say circle plus square does not equal triangle, right? But I see their purpose. It does connote things quickly. But there are a lot of different directed acyclic graphs in the world. Okay. How about surviving missing data, a brief guide? That is a funny character. That looks like, yes, check. I want a brief guide. That is a copy and paste mistake. I copied these slides from PowerPoint and left a character. All right. So missing data can alternate your analysis results. We just talked about that based on the type of missing data, which you'll never know, and the analysis algorithm, how you deal with the missing data, which you have control over, right? So the choice of algorithm or missing data method is important in how you model the data. So the worst case scenario we just ended with, what was it? Minar? Is that what you wanted to call it, Bill? Minar. I like it. Minar. Missing not a random. I feel like you have to be clairvoyant. What's causing this to happen? Like the election example, the polling error, I feel like that's sort of not like most of your data in the world anyway. Now, if you live in that world, that is your world. Okay, cool. But I'm talking about like your big outcome is whether or not you're going to vote for a given individual. It's like a single outcome. I know you have to answer a lot of other questions. Those are auxiliary variables in the terminology of this, right? How often do you just are interested in one outcome? Very, very seldom, right? But with that one outcome, that made it easy to sort of identify where some of the problems were in your analyses. If you're in the real world and you've got your data and you've got 5 outcomes and you have, can you pin that down easily? It's a lot harder, right? So in my mind, like the research that was done in polling data is neat to see because people are like, oh, this is where the problem is. Here's a remedy. We'll see if that works. There's another remedy. But it's still like, even this year, people were saying there's still going to be polling error. People are overweighting or underweighting or doing whatever. It's subjective, right? You're going to have lots of different people with lots of different feedback to it. So if you start getting into MNAR, I can do that. It makes it difficult. Like your choice of how to handle it is not likely to be uniformly agreed upon by everybody. It's probably not going to be agreed upon by anybody, including your mom, probably, right? I've mentioned moms before, but like even your family would be like, oh yeah, but didn't you include this, or how did you create that? So that's where I'm like, you have to be clairvoyant. Like you gotta like have this omniscient like sense to you that you know why that's missing. And I don't know about you, especially as I get older. When I was younger, I might have been clairvoyant. The older I get, the more I knew back in the day. But good luck, right? It's just not. It's something that I think I'm telling you that you're going to never be able to fully satisfy that, right? So there's only so much I can teach you about that because it's going to be very idiosyncratic to your studies that you're trying to do because the mechanisms of missing this, what you're not collecting may differ widely. So, and I mentioned this, algorithms to analyze data, like, so for instance, we could come up with a model for the missing data, like a secondary model, auxiliary model. I believe the book might have called it a nuisance model, something along those lines, right? So what is that model doing? It's basically saying, based on all this other stuff, I'm going to impute the data like this, and then I'm going to run my analysis algorithm itself. So our analysis algorithm have to incorporate a missing step and then the algorithm itself. But like every model, that model has to be right. And the more that you chain an algorithm, it's like, well, I've got missing data here. Oh, I got an idea. I'll put a model on the missing data. Great. Is that model right? Does that model have missing data? Because guess what happens when you put a model on the missing data and it's wrong? What you put in is wrong. If what you put in is wrong, what you get out is going to be wrong. So there's a whole lot of problems with missing not at random. And so what I'm going to try to tell you is this is sort of the cop out, but this is my way of saying I can't tell you all of them. I think in chapter 9 there's some examples of where and how people have handled it in certain situations, but they're not generalizable, right? Like each of our use case will be a little bit different. Yes. I don't know. That will depend on how good the nuisance model is. Right. You could absolutely try, but simulation, the problem with simulation is you have to know what you're missing to build the simulation parameters. So you could come up with a scenario that says, if this is why it's missing, here's what the simulation. So you could do a simulation to sort of test it, but again, you're likely not to understand it in data. Like another reason the polling situation may be different, although not perfect, is that we do this all the time, right? We're sampling people fairly regular intervals. Now, in presidential elections are 4 years apart in this country, but we have midterm elections every 2 years. There's polling in that as well too. So what I'm saying is that's a scenario where you could come up with a hypothesis for what's missing and see if it's borne out by subsequent data that's somewhat proximal in time, unless, of course, a major event changed the electorate between times, right? In my studies, it's not like that. I don't normally collect data with that long where I could even evaluate whether the missingness is sort of working, right? How accurate I'm getting based on my missing model. So it's just hard. I don't know how to describe it, right? So the reality of it is, missing not at random doesn't have an answer. That's what I'm saying to you. Or the answer that you come up with will be highly subjective. That's probably a better way of putting it. The reality is, for most empirical studies, missing not at random is not even considered as a plausible outcome, right? You pull up data analyses and empirical journals from many different, I'm familiar with more of the social science and educational fields. If you see anything about missing, it's usually imputation or maximum likelihood, nothing else, right? And I think part of the reason for that is, so it's impossible to know definitively whether your data are missing, or missing not at random, or missing at random, right? So if you don't know if you don't know definitively, you're left with like missing not at random is impossible to solve. So let's put that to the side. You're left with two choices: MCAR or MAR, right? Well, it turns out methods for MAR are no longer subjective; they're highly uniform. We follow a certain protocol for it, so it's like an established science, right? So in many cases, we treat our data as missing at random, and we model data, we incorporate missing data methods that handle missing at random, because those methods are resilient, or do a better job if the data were actually missing at random, which is probably semi-true, than if they were assuming missing completely at random. If you have missing completely at random, if you just use methods that work for missing completely at random, but your data aren't, bad things happen. So it's like we're doing the least amount of harm by building in our missing data methods for missing at random. Now, I will say there's this little test for missing completely at random. Again, I don't recall ever seeing in print someone trying this. I know people have. I have like all of us, I have a narrow focus on what my research I read about happens to be. But the times I have seen it, it's usually rejected. Yeah. Mm-hmm. Mm-hmm. Probably, yeah. I don't know about dealing with. You could come up with a development for where it is, but it'd be very difficult. Yeah. That's right. That's right. Mm-hmm. Questions on that? So again, we're going to work with pretending data are MAR. If they're not, if they're worse, if they're missing not at random, It's truly non-ignorable missingness, but we're going to ignore it. That's usually what happens, right? And we won't know the difference. So that's how it's structured. The best case scenario is MCAR, not going to happen. But again, the middle ground, MAR, this is what we're sort of the bulk of the book is on. The bulk of what I'm going to teach you is about. We can develop maximum likelihood for most of what we do, even if you have really esoteric models that no one ever uses except for you. Believe me, I've been there. Yes, that's me. You can develop likelihood values for that too. All right, you want to see what happens when we use some of these outdated methods? These are ways not to do it. So I think the last book, he had several chapters on this. This time he's condensed it into a very, very, I'd say chapter 1 was very packed. It had a lot of topics, somewhat different too. I kind of like the way he did it because I think he's the book is completely evolved also. It's not one of these revisions where they fix a few paragraphs and call it good. He's really reworked things. But I find that these are fun. I say they're fun because, yeah, I've done them. Yeah, I had to. And yeah, people still do it now, but let's not do it. Each of these methods, please don't do after this class. All right? I guess I'll put a caveat there. If you're working with an advisor who doesn't know any better, you probably need a polite way of saying you're wrong, right? You know how that works. I struggle with that. I still struggle. I'm never going to fix it. I'm at the age where it's not going to change. But just realize what's happening in the data. And this is to show a little perspective. First is deletion, right? I always love that. Hey, if the data don't work right, get rid of it. Problem solved. In the measurement world, we call that the Roche model. I'm just kidding. The data don't fit the model. It's not the data's problem. It's not the model's problem. It's the data's problem, right? List-wise deletions and deletes the entire, if anything's missing, deletes the entire case. Pairwise, usually we don't see pairwise unless it's like a bivariate statistic, correlation, right? So in that case, when you do a correlation matrix, you may have a different n for each correlation because to be included in what's calculating the correlation, you need both x and y. And sometimes people will have x, will miss on x, have y and z, right? And so they'd be included in the x, y and z correlation, but not the xy or the xz correlation, right? So pairwise deletion is bad. Also, speaking of correlation, when you use pairwise deletion and you build a correlation matrix, that correlation matrix may not be invertible. You may be like, why do I care? Because if you're using it with maximum likelihood later on, like a secondary analysis, I mentioned SEM started that way, it needs to be able to invert it with multivariate normal. So true correlation matrices, what we call positive semi-definite matrices, that's a technical term. If you were to take their determinant, that means it's 0 or positive, it's not negative. At 0 is the semi-definite. That's where it's still tough to get an inverse. It's usually, but it's rarely exactly 0, right? So pairwise deletion correlation has problems not just because of bias. If you use deletion methods, you're basically assuming your data are missing completely at random, and if you do that, you get less power. If they're not missing completely random, then bias your estimates. So listwise deletion is deleting all the data. Listwise deletes where independent variables are missing. So X is missing. Gotta fix that slide. Hang on, slide 42. Sorry, folks. I will clean this up and repost it. So we saw that in the example I just ran. Here, these data, I have 13 degrees of freedom when I ran missing at random. And I have 18 degrees of freedom when I have the complete data. So what's happening is it's just removing those observations altogether, right? And actually, that's y, not x, so that's not a good example. Anyway, don't do the, here's listwise, oh, I do have this listwise deletion here. And these are the results I just showed you. It's like I made these slides, I just totally forgot it since then. In my defense, I did make lectures 2 and 3, but can I digress for just a moment? So you got to send your professors like your master's thesis or your dissertation or whatever. Like if you're going to have your dissertation defense or your comps defense, you send something to them, and like you got to give them 2 weeks to read it. At my age and many of my colleagues' ages I've talked to, well, at least one key colleague I happen to live with, um, we get to the part where if we read it 2 weeks ahead of time, we're not going to remember what's in it because we usually have to read lots of things. So we read it the day of or the day before because then it's fresh in our mind. Case in point with the slides. I apologize. Absent-minded professor is real. I think I was absent-minded even without being a professor. So it just happens. But here's that example. I am recording, and I'm on record saying it. If I can't be critical of myself, I can't be critical of you either, right? So hopefully not critical of you in the sense I can't grade you. How's that? Have some grace. All right. So here, I don't have either. This is okay. So this is the complete data over here. This is missing completely at random. We saw the difference between here. Although I did estimate this, the maximum likelihood does not have IQ as a predictor variable in the likelihood itself. So this is Levon estimating this, but because I left IQ out, it's not part of the likelihood function, so it's not getting that maximum likelihood benefit that we're talking about. And here, the complete data estimate for the slope was 0.103. For the missing completely at random, it's 0.167. The intercept really changes. So a little bit of example. And here's your missing at random version as well, too. All right, I'm going to skip off of that because I don't know that that's really that informative. I thought it was informative as I was putting it together, but then as I'm telling you now, I'm like, maybe not. You ever done that before? You ever taught a class and you're like, oh, this is really important, and then you get to class and you're like, actually, that was a terrible idea. I'm recording this too. That was a terrible idea. All right, pairwise deletion. This is, here we go, correlation. So you can use pairwise complete obs in your correlation function in R. And this is the correlation between IQ and the complete data here. And then IQ and completely at random or missing at random. And again, it's hard to tell with this data because these aren't, I don't know what the right answer would have been. I guess the closest right answer is 0.54, but then again, we have a higher correlation with the missing data, missing observations, which can happen. That's a bias. It doesn't have to always be biased negatively. Okay, single imputation methods are also bad, right? Single imputation means you have a data set, you're just going to make it complete, one way or the other. The nice part of that is you can use your full data set. The downside is by method that you choose to complete your data set, you may inadvertently bias your parameter estimates, right? So bias parameter estimates, you may also shrink your standard errors more than needed. So you may end up having type 1 error rate issues. So the most obvious is the unconditional mean imputation, which means it imputes the mean without input from any other variable. So here, that is what I did. I took the missing completely random data. I imputed for job performance all of the values that were missing, and then of course I screwed up the regression here. I predicted IQ by performance, not performance by IQ. Anyway, I'll just go through this. Actually, no, I won't go through this. I can fix this. Gosh, Jonathan, I'm sorry, folks. Unconditional mean right here. This should be, that's my imputation. And this should be the other way around. Fix this. All right. So if I do that, let's just take a second to recalibrate. And now, here we go. Let me make this a little bit bigger. I am sorry about that. Oh, and I cannot make it bigger. I can make it bigger right here, though. There we go. Is that a little bit better? Okay, let's see what's happening here. In the complete data, again, I'm not getting a lot of good estimates with this here, but yeah, point estimate of intercept and IQ. My point estimate of my intercept has changed considerably. My IQ slope has shrunken. What I was really trying to show is the standard error was lower. But what you can say here is the following. Look at my R square for my model. With complete data, it was 0.29. And when I just gave everybody who was missing job performance the mean, it shrunk, right? So that's what's happening. And I think the book had a plot of that, right? You put a pile of people at the mean of one of the variables, it changes the whole relationship. Does that sound reasonable? Hope so. And the same thing here, missing at random. So it turns out, even if your data were missing completely at random, this is a bad idea, right? It's bad because you're imputing your data with a single value, and that single value is not what you expect it to be. It literally shrinks the variability, right? And you can also think about that from the concept that I was trying to get across the first week of class, which was that the trick to missing data is thinking that the missing data follow a distribution. When you put a single value in for everybody and it's the same, that's ignoring the distribution of the data, right? You're just imputing a valid data point. And so here's the difference. This is the complete data right here. This is our original estimates. Oh, no. And then these are our missing at random values. And again, here you will see, well, I don't have it here, but basically the same thing happens. The R squared is shrunken. We don't have as good predictive power. So that's not good either. Like, we don't want to inflate R square artificially. We also don't want to shrink it artificially either, right? We want to make sure it's somewhat accurate. So listwise and pairwise deletion, bad ideas. Actually, this was what I was looking for right here. It was unconditionally marred versus complete. Did I not do that right also? 1 second, please. Yeah, I screwed that up. This is especially challenging with my left wrist, but come Friday, my left wrist gets freed, I think, unless I did something else that's messed it up. So next week, this will go faster. 550. There we go. Yeah, our R squared is still, this is what I was after. R squared is still small right here, right? Bad idea. And it's still small over here. Still not there. All right, I'm completely messing this up. The alternative to that, so someone would say, great, unconditional mean imputation, not a good idea. I'm going to use a regression line. I'm going to impute everybody's predicted value from a regression. Actually, in my early days of being a professor, I remember working with a colleague and they were like, oh, I'm not doing mean imputation. But it turns out when you do that, you are doing mean imputation. It's just conditional mean imputation, right? The mean of performance conditional on a person's IQ. So you're still doing single imputation. It's a mean. It's probably a little bit easier to see than to work. It's probably a little bit better than unconditional mean, but in the space of things to do, please don't ever do that, right? Unless, of course, your advisor tells you to, and you need to stay employed. When you're your own advisor, please don't do that. How's that sound? So people thought, wait a minute, regressions, this is a regression line right here. When I form a linear regression, I add error to it. I can quantify that error. That's my residual mean square, right? Mean square error, or a point estimate of it if we're using maximum likelihood. What if I draw a random observation from a normal distribution where the variance is equal to my residual mean square, or a variance estimate? So that is stochastic conditional mean imputation. And that is getting even closer. But the problem with it is now, okay, so you think of that distribution of data, think of our distribution of the propensity of what scores should be. This is now getting even closer. It's trying to draw from it, but you've only drawn once. So that's subject to having problems in that if that draw is wrong, if that error, that stochastic error that you've added to everybody is off, it's going to show up in your results. It's going to bias your results. This, by the way, is the starting point for mice. Right? I mentioned the chained equations. Basically, the chained equations goes through iterations of stochastic mean imputation throughout. And it's a long process, almost like a Markov chain, where every missing observation gets imputed using stochastic mean imputation. And then that results in a set of data sets that you can then use to analyze your data. So. Then there were some other fun ones, something called imputation by proximity. So if you looked at a person's data they did have, and you tried to figure out who in the data also had scores that were similar, right? So if you had variable X, Y, and Z, someone didn't give you X, but they had Y and Z, you look at the people who were closest on Y and Z, and you figure out what X's they had, and you give this person an X, right? They called that hot deck matching, which really, I don't know where the hot deck comes from, but sure. It must be a term I wasn't familiar with in my childhood. The neat thing is it's using real data, but you can imagine how that's going to be, right? Right? Think of it this way. Let's imagine I want to model, this is a very personal example, cardiovascular risk based on my BMI, like my height and my weight, and somehow I didn't step on the scale, or the scale glitched, so they had my height but not my weight, right? So hot deck matching would say, oh, let's find everybody who's the same height as me, like 185 centimeters, right about 6'1", just about. All right, in my data set, I've got 3 people who are 6'1". Let's impute his weight. Well, I'm probably heavier than all of them. Right? So you know how that's going to be. They're going to take one of those weights and give it to me. Probably not going to work, right? But that's what it happens. Its upside is that it helps preserve univariate distributions because you're drawing data from the same distribution of like weight in that example. And it also gives you data in appropriate range, right? You can think of what happens if I'm telling you that stochastic conditional mean imputation is the basis for mice, for chained equations. You can envision, depending on your model and your data, you might impute data that's out of range altogether, right? Depending on how you built the model for it. We'd like that not to be the case, but it could be. Hot deck matching removes that problem, so that's a good thing. But yes, you're going to get bias and 2 small standard errors, so don't ever do that. Bad, right? Because you substitute the idea that there's a distribution of my missing data for saying, no, I know what it is. It's someone else's data. Treat me like I'm somebody else, right? Which we know that's probably not going to go very well. This is a good one. Scale imputation by averaging. Let's imagine you give out a survey. Liquor dive. Hey, at the end of this class, you're going to rate me on a survey. Please rate me well. But no, just kidding. That's not the point, right? If you omit one of those questions, what happens? Well, in our case, we ignore it. But if you wanted to, let's flip the other way around. If you wanted to come up what a person's average for that would be, right? You might sum together a bunch of items. Let's just think of the easy way of doing it, classical model for it, right? We sum up our Likert items. But if someone didn't give you one of those responses, what do you do with them? Because their sum is not out of the same total now. If you had 5 items, they were all 5 points each, 1 through 5, your total would be 25, right, from all 5. Somewhere between 5 and 25 is the range of the score. But if someone omits one of those items, their range of the score is 4 to 20. So what do you do with it, right? A lot of times people would go and take the average of the item they missed and impute it for that person. That is unconditional mean imputation, right? The other way people try to do this is take a proportion, right? So what's your proportion out of your range? Well, that also assumes a constant proportionality for the item that's missing, right? Basically, that your score on that would be sort of ignorable. So you know what happens there, right? That it reduces standard errors, it makes calculation of reliability bias. There's all sorts of bad things. We don't want that to happen. And if you got longitudinal data, some people used to think, oh, let's take our carry forward our last observation, right? So remember Y1, Y2, Y3, Y4. If someone gave you Y1 and Y2, but not Y3 and Y4, and let's imagine this was a treatment for, some type of treatable disease, right? Where you're progressing and getting better. If you stop the study at the second time point, we have no idea if you're getting better or worse. Right? You may still continue to get better, but carrying that second time point score forward does two things, right? It flattens your variability of your across your entire range, but it also assumes that like you're not going to change. That latter part seems pretty good. It seems pretty conservative, right? Well, let's assume no change. But by shrinking your variability for what your scores could have been, you potentially reduce the standard errors in your sample and your model. You can exaggerate group differences because within if you have more dropouts in one group than another, one group's standard error will be smaller just as a function of having a constant for every variable that you've imputed. That smaller standard error for the group makes it look like standardized group mean differences may be bigger because the contribution to the standardization, your pooled variance is smaller from one group. So bad science. I hate to say this. I made this slide many years ago thinking about the community I was in. It's not good to do. Single imputation, not a good idea. Reduces the range, reduces your standard errors, leads to type 1 errors, make bad conclusions. And yet, what did I say about test scores? They're all single imputation. Bad idea. So, test score itself is fine. I always want a standard error. I annoy people. Like one of our former colleagues worked with ETS, and they wanted to know what faculty wanted to make GRE more relevant. And I kept saying, I need a standard error. Someone gives me a GRE score, that's fine, but what's the error around it? Now, we can't do that. Well, actually, you can. I need to know how much error there is. But yeah, single imputation, bad idea. It is not what we're going to do. So, any questions on these old methods? I thought I'd throw them in here for fun. I've probably done most of them. I haven't done hot deck matching, although I wish I would have, because that sounds like I don't know why hot deck is there. But any questions? Are we good? Was the book convincing with the pictures? Like where the data look and like how it changes things? I thought it was a pretty nice demonstration. So, all right, that's it for today. Lecture summary. We're going to pretend everything's missing at random for most of what we're doing. More often than not, ML is best choice. I wouldn't say that. We're not really going to, again, missing at random, we can use three methods: multiple imputation, maximum or likelihood based, which is maximum likelihood or Bayesian. Which one of those three is usually dictated by how much patience you have to do it. But I'm going to give you all three. Next week, we're actually going to discuss the precursors to maximum likelihood. So I want you to read chapter 2 first week. The quiz questions will be about chapter 2. Actually, we'll have 2 weeks of quiz questions about chapter 2. So chapter 2 next week, you don't have to worry about chapter 3 after that. We will talk about the building blocks next week. We're going to talk about joint, conditional, and marginal distributions. We're going to talk about PDFs, likelihoods. So we're going to talk about how to build a likelihood function itself. Those are terms that many of you may know, but I just want to cover it again. At the very least, you'll get it from my language, because we sometimes describe things a little bit differently. But that will set the stage for us learning how to use existing maximum likelihood software for joint models, or how to build potentially likelihood functions for not joint models, to which point then you'll go into Bayes and think Bayes is so much better because it's easier in some ways. And then we'll move forward into multiple imputation. Does that sound okay? And that describes like from here to spring break. Okay, any questions? Anything else? You get a few minutes back. So have a great rest of your afternoon. If you have questions you would like chat after class, I'll be here for a few minutes while I shut down. And otherwise, you know where to find me. Please do reach out if you have anything you'd like to talk about. Thank you. Thanks for coming. Have a great rest of your week.